In the heart of one of the most unforgiving environments on Earth, a battle has been raging, not against armies, but against the elements. Saudi Arabia is investing $22 billion to carve a railway through the vast desert, linking critical parts of the kingdom in reshaping its future. The goal? To ease traffic, reduce pollution, and create a modern, connected city in Riyadh, a place where summer temperatures soar past 50 degrees Celsius, and sandstorms can halt progress in an instant. Yet with obstacles ranging from political upheavals to supply chain breakdowns, will this ambitious project stay on track, or will the desert prove too powerful to conquer? A city built on sand, Riyadh has grown at an astonishing pace, but its rapid expansion has come at a cost. Traffic jams snake through the streets, suffocating the city in a haze of car fumes and congestion. In a place where temperatures can roast the streets to over 40 degrees Celsius, walking is almost unthinkable. The city's dependency on cars has become more than just a convenience. It's a way of life. Yet, as Riyadh's population swells beyond 7.5 million and heads towards nearly doubling by 2030, this heavy reliance on automobiles threatens to choke the city's progress. For years, Riyadh's urban sprawl stretched outward without a cohesive plan for public transportation. Cars dominated, and the city's infrastructure reflected that. But as traffic congestion became unbearable and pollution levels soared, it was clear something had to change. Enter Vision 2030, Saudi Arabia's bold plan to overhaul its cities, economy, and future. At the heart of this vision is a transformative solution to Riyadh's growing transportation crisis. A $22 billion metro project that will span the entire city and revolutionize how its people move. Picture Riyadh as a blank canvas, now crisscrossed by 6 new metro lines, stretching 176 kilometers in total. These lines weave through the city from the airport in the north to major business hubs in the south, connecting universities, financial districts, and key residential areas. With 85 stations dotting this vast network, it's designed to make travel more accessible and efficient for millions of residents. Whether you're moving from King Khalid International Airport, heading downtown, or commuting to King Abdullah Financial District, the metro will take you there. The challenges, however, are equally immense, constructing a metro in a city where the desert itself fights back. And that's where this story gets truly interesting. How do you even begin constructing something this ambitious in such harsh conditions? The design and construction of tunnels primarily employed the sequential excavation method, or SEM, also known as the New Austrian Tunneling Method, or NATM. This method allowed the engineers to use the ground's natural load-bearing capacity, making the tunnel excavation safer and more efficient. The key to this method is carefully balancing excavation and support to maintain the integrity of the surrounding ground. But even with this efficient method, the engineers faced significant challenges from the start. The first issue they encountered was Riyadh's complex geological makeup. The tunnel alignment cut through the city's carbonate rock formations, including the Sulai, Arab, and Jubalia formations. These layers are composed of limestone, breccia, and anhydrite, all of which present varying degrees of strength and stability. The Sulai formation, found near the eastern portion of the tunnels, is predominantly limestone, while the Arab formation, which dominates the alignment, consists of disturbed and undisturbed beds of limestone and anhydrite. These formations are prone to dissolution cavities, voids formed by the natural dissolution of rock through groundwater flow. These cavities posed a major risk as their presence could lead to tunnel collapses or destabilization of the structure if not properly addressed. As the tunneling progressed, the engineers had to constantly probe ahead of the tunnel face to identify these hidden cavities and weak rock formations. Probing allowed them to take immediate action, whether by reducing the excavation length, installing extra support, or filling the cavities with grout. In these sections where the rock was highly fractured, the engineers employed rebar spiles, steel rods inserted into the ground above the tunnel to reinforce the rock and minimize movement. Groundwater management was another critical challenge. The tunnels, especially in the western portion, passed through areas where the groundwater level was significantly above the crown of the tunnel. This posed a constant risk of water inflow, which could flood the tunnels or destabilize the excavation process. The engineers had to carefully monitor groundwater levels and install dewatering systems to keep the tunnels dry. In some cases, they converted probe holes into dewatering points, allowing water to be drained before it entered the excavation site. Additionally, drain mats and flexible hoses were installed to collect localized water inflow, channeling it into sumps located at the base of the tunnels. One of the most complex sections of the project involved tunneling under existing structures and foundations. The Line 2 tunnel alignment passed directly under building foundations and a viaduct pier, which meant that even the smallest ground movement can have catastrophic effects on the buildings above. To minimize ground movement, the engineers reduced the round length of the excavation, ensuring that the support system was installed almost immediately after each section was dug out. In areas where future construction was planned above the tunnels, the engineers used glass-reinforced plastic or GRP dowels instead of steel to make it easier to break out new tunnels without damaging the original support structure. Perhaps the most impressive feat of engineering occurred where the tunnel passed under an open-cut excavation for a large commercial building. Here, the tunnel's crown was almost at the surface, leaving minimal cover between the tunnel and the ground above. To ensure the stability of the tunnel, the engineers designed a temporary roof structure, affectionately referred to as the turtleback, which acted as a protective canopy over the tunnel. This roof was cast in concrete and reinforced with wire mesh, forming an arched lid over the tunnel that allowed excavation to continue safely below. The use of modern materials and technology also played a crucial role in the project's success. The primary lining of the tunnel consisted of steel fiber reinforced shotcrete, which provided immediate structural support as each section of the tunnel was excavated. This was formed by the installation of rock dowels, steel rods inserted into the tunnel walls to further stabilize the ground. In better ground conditions, the engineers were able to extend the excavation round length to 3 meters, speeding up the process without compromising safety. The secondary lining was a cast-in-place concrete structure, 300 millimeters thick with a waterproofing membrane sandwiched between the primary and secondary linings. This membrane ensured long-term protection against water infiltration, a critical factor given the high groundwater levels in certain parts of the tunnel. Fire safety was another consideration, especially in a city as hot as Riyadh. The secondary lining was designed to withstand at least 3 hours of fire exposure, with polypropylene fibers added to the concrete mix to prevent explosive spalling under extreme heat. These fibers melted in the event of a fire, creating pathways for steam to escape, which reduced the risk of the concrete breaking apart. As the excavation progressed, monitoring systems were put in place to track ground movement and ensure that the tunnel remained stable. In-tunnel convergence monitoring points were installed at regular intervals, measuring even the slightest shift in the tunnel's walls. Above ground, automated total stations and optical targets were used to track any settlement or movement in the buildings and structures above the tunnel. This constant monitoring allowed the engineers to adjust their excavation methods in real time, ensuring the safety of both the workers and the city's infrastructure. During the summer months, temperatures often exceeded 50 degrees Celsius, making it nearly impossible for workers to operate safely during the hottest hours. Sandstorms frequently disrupted operations, and in the winter, the desert cold presented its own difficulties. The materials used had to be carefully selected to withstand these temperature fluctuations, ensuring the longevity of the infrastructure. Concrete, for example, dried too quickly in the heat, leading contractors to modify how it was stored and poured. But even beyond the physical challenges, there were delays and disruptions due to external factors. The former governor of Riyadh was arrested during a crackdown on corruption in 2017, impacting the metro project. Then came the pandemic in 2020, which caused significant supply chain disruptions. Now, with the tunnels complete, the next challenge looms. Will the Riyadh Metro meet its ambitious goals and open on time? Or will further delays and complications push this massive project even further into the future? Thanks for watching. Don't forget to like, subscribe, and hit the notification bell for more updates. Let us know in the comments. Will you be riding the Riyadh Metro?